Okay, guys, so let's continue with some other theorems related to the sample variance, sigma s squared. So actually, we cannot directly use the above theorems related to the distribution of sampling distribution of s squared. So the sampling distribution of capital S squared does not follow directly from the above theorem, because in the above theorem we are using the independence of random variables, but when we consider the form of the sample variance, we have the terms xi minus x bar terms. And these are not independent from each other. If you consider the covariance, these terms are not independent from each other, are not independent. Okay, so we cannot use the exact same results of the theorem, above theorem, because when we consider x1 and x bar, actually they are related to each other. So in x bar we have all x values, so they are kind of related to each other. But luckily we have a good property of those summation xi minus x bars. So when we sum them up, actually we should end it up with 0. So this is the good property, but they have to obey the fact, which is summation of xi minus x bar. So this should be 0 over all sample values. Okay, so we can use this. So this is a good property of that we can use to find the sampling distribution of s squared. So we have a theorem with 3 sentences. If x1 to xn are forming the random sample, so they are identical independent random variables from normal with mean mu and variance sigma square, then the first condition, x bar and the terms x1 minus x bar, x2 minus x bar, xn minus x bar, they should be independent. So we will find a proof. So you know how to show that 2 variables are independent from each other. So using the first theorem, we can also prove that x bar and s square are independent, because in s square we have all xi minus x bar squares. If x bar and xi minus x bar terms are independent, their square will be independent. Some of those squares will be independent. So using that, we can show that proof. And the last one is about the kind of sampling distribution of a function of s square. So this has chi square with n minus 1 degrees of freedom. Okay, so let's prove all these. So start with the proof of 1. After showing the proof of 1, immediate proof comes for the second one. So how can we show the independence of random variables? Do you remember? Okay, we cannot use correlation or covariance because they only show the relationship between 2 random variables in a linear fashion. So if we have a nonlinear relationship, we cannot actually state it by just looking at the correlation or covariance. So one thing to say is about the joint distributions. If x and y are independent, or these are independent if and only if we can write the joint distribution of x and y as a multiplication of two marginal distributions, okay? Or what we can say, conditional distribution can be written like that, okay? But we will use the first one, the joint distribution can be written as a multiplication of 2, okay? So here we will use this to prove the theorem. Okay, so let's start with the given information. So what we know is x1 and xn are random sample from normal distribution. So let's find the joint distribution of this random sample, and then using the transformation techniques try to show that x bar and the other terms are independent. Okay, so let's start with, so we always start with the given information and then convert it to the things that are asked in the question or whatever our problems of x1 to xn. Okay, so since we have a random sample, then the joint distribution of x1 to xn, because they are independent, because they are random sample, we can write this as a multiplication of marginal distributions of x1 to xn. Then using the properties of normal distribution, PDF of the normal distribution, x1 minus mu whole square divided by 2 sigma square, and 1 over 2 pi sigma square e to the minus xn minus mu whole square divided by 2 sigma square. So when we combine all, so what we will have, 2 pi sigma square and over 2 e to the minus summation xi minus mu whole square divided by 2 sigma square 1 from n, and each xi between plus minus infinity. Okay, so we know this information. So this is the given information. So this is the given info. Okay, then let's find the joint distribution. So what we need to show, actually, to be able to show, then using this, we need to show joint distribution of x bar and all these can be written as f of x bar and the joint distribution of x1 minus x bar to xn minus x bar. Okay, so all our aim is to be able to write this PDF in the other one, but all we know is this actually. Okay, so how can we do that? So now let's first find the joint PDF of y1 equals x bar and the others. Okay, so I will use y2 equal x2 minus x bar and yn equals xn minus x bar. Okay, so here we skipped using, so here we didn't use x1 minus x1 term because it's a redundant information. So we know that because we know that sum of xi minus x bar terms will be 0, right? If we have all the others, the one of them should be a fixed quantity, so it's not a random variable anymore because of this restriction. Okay, so here we choose x1 minus x bar, but if you want you can choose x2 minus x bar or xn minus x bar, whatever you want. I choose the first one. Okay, so because of this rule, we don't use one term. Okay. We do not use one of the xi minus x bar term. Okay. Then, so what is our aim now? Our aim is to prove or show that f of y1 to f of yn can be written as f of y1 times f of y2 to 3 dots yn. Okay, how can we do that? First of all, we need to find the joint distribution and then look at the form of the joint distribution, if it can be written in this form or not. If it can be written in this form, just one function related to the distribution of y1 and the others related with the other one, then we are good to go. Okay, so using the joint PDF of x1, because we only know this information, we need to find the, first of all, joint PDF of y1 to yn. Okay, so we need a transformation technique here. So since we know the forms of the equation, so it's better to use Jacobian technique here. Okay, so our first y1 equals to x bar. Okay, so we can write this as x1 over n plus summation of all other xi values, which is starting from 2 to n. Okay, then we will try to write x1 as a function of other y's, but at this point it's better to find the other x2, xn values, and then we can replace this sum by other y values. Okay, so then we can write y2 as x2 minus x bar, but our x bar is just y1, so from here we can write x2 as y2 plus y1. Similarly, we can do all other y values. X bar, again this will be y1, so xn can be written as yn plus y1. Okay, so using all these, what we will get when we sum all the x2 xi values I from 2 to n, what we will end up will be summation of yi values, I is from 2 to n, plus n minus 1 y1 term. Okay, then in the y1 formula we have this x1 over n plus, instead of the sum, summation yi plus n minus 1 y1 2 to n over n. Then our x1 can be written as n times y1 minus summation of I from 2 to n. Okay, so we can write x1 this way. Okay, then so we are doing transformation, so we are changing the dimensions from x to y, so we have to use some adjustment, which is done by Jacobian matrix. So we need to use the absolute value of the Jacobian matrix to adjust the dimension. Okay, so the absolute value of the Jacobian matrix from x1 to y1, get the partial derivatives for each xn to y1 and xn yn. So what we will get here, so we will have 1 minus 1 minus 1 minus 1, the last one. Then we'll have 1 1 0, all the others 1 0 1, all the others 0. Okay, so it will go like that, 0 0, the last one will be 1, and when you calculate this you will get n. So we have to use this also in the joint distribution when we convert our distribution from x to y. Okay, so the joint distribution of y1 to yn then equals to joint distribution of x1 to xn times the Jacobian. Okay, so instead of these x values, x1, xn values, we will convert those, we will use these x values in terms of y's. Okay, then because we know that we have random sample independent random variables in terms of x, so they can be written as f of x1 times. So what was the value of x1? y1 minus summation yi, I from 2 to n. Okay, then f of x2 equals to y2 plus y1 and the xn value yn plus y1 multiplied with the Jacobian. Okay, then we know that each one is normally distributed, so we have 1 over 2 pi sigma square in the square root e to the minus y1 minus summation yi, I from 2 to n minus mu whole square divided by 2 sigma square, the first one. And then we have the similar ones, e to the minus, but instead of x2 we have y2 plus y1 minus mu, take the square, divide by 2 sigma square, multiply, continue here. So we have the last one, 2 pi sigma square and the square root e to the minus yn plus y1 minus mu whole square divided by 2 sigma square, multiply with the Jacobian n. Okay, so when we combine everything, so we will end up with n over 2 pi sigma square n over 2. Okay, e to d, we are using as x notation, if things are too long. Okay, then we have n times. After opening these all square terms, okay, or after expanding all these, so we will end up with this. Plus minus yi whole square, I from 2 to n, plus summation yi whole square, I from 2 to n. Here at this point we have some other terms actually, but when you look at those terms, when you open up everything, we will end up with 0, so they are not included in the above form. y2 and then 2 times y1 minus mu yn. When you open everything, you will end up with 0. Okay, so our main equation is the above one. Okay, then we can write our joint distribution from y1 to yn as, okay, so what's our aim? To be able to write our joint distribution as a multiplication of y1 and the rest. Okay, so let's try to separate y1 term from the old equation, and then let's see we have in the y1 term that cannot be separated from all other y terms, y2 to yn. Okay, so let's combine everything with y1. Okay, so let me write this part, 2 pi sigma square. Then we have e to the minus n, y1 minus mu whole square divided by 2 sigma square. So we have this one, and we have the other part, 1 over 2 pi sigma square, let me put it in parentheses, and minus 1 over 2, and e to the minus summation yi square plus minus summation yi whole square. Here I is from 2 to n, I is from 2 to n, divided by 2 sigma square. Okay, so here as you can see, we can be separated all the terms, y1 terms, from all other parts. So we have one function for y1 and another function for other y values. So this is the marginal distribution of y1 part. and this is the joint distribution of y2 to yn. Okay, and if you remember, y1 is actually x bar, and x bar should distributed as normal with mean mu and variance sigma square over n, so we have the same form. So this is the PDF of PDF of y1. Okay, so this means that we could write the joint distribution as a multiplication of 2. So here's y1, which is x bar, and all other xi minus x bar terms, I from 1 to n, 2 to n, sorry, are independent. Actually 1 to n, because we omit 1, but it's actually redundant kind of observation. So are independent. Okay, so this is the proof of the first one. Then the proof of the second one. Actually this part just follows the above proof, part 1, because the form of the mathematical form of the standard deviation is a function of oops, I should write function of, okay, only xi minus x bar. Remember the form of the xi term, s square term. So then because of the independence of x bar and other value xi minus x bar terms, s square, which is a function of xi minus x bar terms, should be independent. I is from 1 to n. Okay, and then proof of the third one. It's about the distribution of sample variance, the function of the sample variance. But okay, so again here let's start with the known information from the previous proofs, previous theorems. Let's start with the known information related to the variance. Well, so what we know about the variance form, so we know that summation xi minus mu whole square I from 1 to n divided by sigma square distributed as chi square with n degrees of freedom. So we know that. We already proved that. Then try to write the summation xi minus mu whole square as a function of s square, because we want to find the distribution of function of an s square. How can we do that? Okay, so in the s square formula we have xi minus x bar squares, but we have xi minus mu. If we add and subtract x bar term, then we can catch s square form by the given information. By adding and subtracting x bar term. Okay, so we have summation xi minus mu whole square, then xi subtract x bar, add x bar mu square, and then separate expand the square. So we have xi minus x bar whole square plus n times x bar minus mu, we don't have any increment, plus we have 2 times x bar minus mu and summation xi minus x bar. But we know that this part is 0, so summation xi minus x bar whole square can be written as summation xi minus x bar square plus n times x bar minus mu square. Okay, so then Again, oops, this should be mu. Sorry about that. Xi minus mu whole square divided by sigma square. So we know the distribution of that. So let's divide both sides by sigma square. Over sigma square. So we know that this has a chi-square distribution with n degrees of freedom. Again, we use the theorem and we know that this has chi-square with 1 degrees of freedom. So using this, we need to find the distribution of this part. So let's say this is V1, let's say this is our V2, and let's say this is our V3. And we need to find the distribution of V3. Okay, so we have the chi-square distribution, and we know that the s square and x bar terms are independent from each other. So using the independence of s square and x bar, we can write the moment generating function of V1 as a multiplication of V2t multiplied by the third one, MGF of the third one. Okay, so here, if you remember, we can write this part as n times, or n minus 1 times s square over sigma square. So actually we have s square here. Okay, summation xi minus s square. So we can write it as n minus 1 times s square over sigma square. So here in the V2 we have s square, in the V3 we have x bar, so these are two independent. Okay, and then we know the moment generating function of chi square with n degrees of freedom, which is this one minus n over 2. So we need to find the moment generating function of the second one, then we can define its distribution by looking at the form of the MGF. So here, moment generating function of the second one, the V2, the 1 minus 2t minus n minus 1 over 2. Okay, so it has the same form of the chi-square distribution. So this is the MGF of chi-square with n minus 1 degrees of freedom. So this means that summation xi minus x bar whole square divided by sigma square, or which can be written as n minus 1 times s square divided by sigma square. This s square is capital, is chi square with n minus 1 degrees of freedom. So this is the end of this video. I will continue with the distribution related with the t, but again our starting point will be normal. Okay, see you in the next video.